Hello, welcome to my video series of data structures. This is part 3 of Module 7, the union-find data structure. In this video, we will discuss the quick union implementation. In the previous video, we discussed the quick find implementation of the union-find data structure. This approach represents a disjoint set using an array A of size n, where n is the total number of elements. Each entry AI stores the label of the set that contains element I. For example, if AI equals J, then element I belongs to set J. In the quick find implementation, the find operation runs in constant time, O1. However, the union operation has an amortized time complexity of O log n over n operations, while a single union operation can still take On time in the worst case. In this video, we introduced the quick union implementation of the disjoint set data structure. This implementation enables O1 time union operation. While the find operation initially runs in O log n time, additional optimizations can make it nearly O1 in practice. Conceptually, the disjoint set structure is represented in the quick union implementation as a forest, where each tree corresponds to a disjoint set. For example, the forest shown here consists of 3 disjoint sets. The first set contains a single element, 2. The second set contains a single element, 5. The third set contains 3 elements, 1, 3, and 4. Each set is identified by its root node. For instance, the set that contains elements 1, 3, and 4 is labeled 3, because element 3 is its root. In our case, there are no specific constraints on the tree topology. Any node within a tree belongs to the same disjoint set. The quick union implementation represents the forest using an array A of size n. Specifically, if an element I is not a root, AI stores its parent node. If I is a root, AI is set to -1. For instance, the array A represents the forest formed by the 3 trees shown here. The entries A2, A3, and A5 are all -1, indicating that these elements are the root nodes of their respective trees. A1 and A4 both equal to 3, meaning that elements 1 and 4 are children of element 3. Let's use a concrete example to illustrate how the quick union implementation handles the union and find operations. Initially, each element forms its own set, corresponding to n individual trees. In the array A, all entries are set to -1, indicating that each element is the root of its own tree. Now, suppose we need to merge set 3 and set 5. Since a set's label corresponds to its root node, the root of set 3 is element 3. To merge set 3 and set 5, we update A3 to 5, making element 3 a child of element 5. This step attaches one tree to the root of the other, effectively merging the 2 trees. Next, we merge set 2 and set 5. Since the root of set 5 is element 5, we update A5 to 2, making element 5 a child of element 2. This step attaches the tree-rooted element 5 to element 2. At this stage, we are not considering the sizes of the sets when merging. Either tree can be attached to the other. Later, similar to the quick-find implementation, we will demonstrate that attaching the smaller tree to the root of the larger tree leads to a better efficiency. From the examples above, we can summarize the union operation as follows. To merge two sets, we update the array entry ASI, where SI is the label and root of one set, to SJ, the label and root of the other set. Such an implementation of the union operation runs in O1 time. Next, let's explore how the find operation works in the quick union implementation. Given an element I, we repeatedly follow its parent node, climbing up the tree until we reach the root. Suppose we need to find a set that contains element 3. We first check A3 and find that it stores 5, meaning element 5 is its parent. Hence, we move up the tree to element 5. Next, we check A5 and find that it stores 2, meaning element 2 is the parent of element 5. We continue moving up to element 2. Finally, we check A2 and find that it stores -1, indicating that element 2 is a root node. At this point, we terminate the iteration and return 2 as the label of the set that contains element 3. Here is the pseudocode for the find operation. We traverse up the tree using the while loop shown in lines 2 to 4 until we reach the root. In this way, the time complexity of the find operation is proportional to the depth of the tree. Since we impose no structural constraints on the tree, the depth can reach On in the worst-case scenario. As a result, the find operation also has a worst-case time complexity of On. Next, we will show that by using a smart union strategy, where the smaller tree is attached to the larger one, we can reduce the time complexity of the find operation to O log n. Let's reconsider the merge of set 2 and set 5. Previously, we attached element 5 as a child of element 2. With the smart union strategy, we always attach the root of the smaller set as a child of the root of the larger set. In this case, set 2 contains only one element, while set 5 contains 2 elements. Since set 2 is smaller, we attach element 2 as a child of element 5. This is achieved by updating A2 to 5, resulting in the updated forest shown below. Comparing the trees formed by the naive union and the smart union operations, we find that the smart union tree is shallower. To efficiently perform smart union, we need to track the sizes of the sets. We store these sizes in the array entries corresponding to the root nodes. Specifically, If Si is the root of a disjoint set with size m, we set ASI to negative m. In this case, a negative value indicates that the element is a root. The magnitude of the value represents the size of the set. For example, here we have A5 equals negative 3, meaning that the tree rooted at element 5, that is, the third tree shown here, contains 3 elements. Here is the pseudocode for the smart union operation. In lines 2 to 4, we compare the sizes of sets Si and Sj, and swap them if necessary to ensure Si is the smaller set. In line 5, we update the size of the merged set Sj as the sum of the sizes of Si and Sj. In line 6, we attach the root node Si as a child of the root node Sj. Since all these additional steps run in constant time, the time complexity of the smart union operation remains O1. Next, we establish an upper bound for the find operation when using smart union. When merging two trees, the depth of each node in the smaller tree increases by 1, while the depth of the nodes in the larger tree remain unchanged. It means that finding the root for a node in the smaller tree requires one additional step. For example, consider merging set 2 and set 5 using smart union. Before the merge, element 2 has a depth of 0, meaning it can reach its root node in 0 steps. After the merge, element 2 now has a depth of 1, requiring one additional step to reach the root, element 5. This additional step occurs because the root of the larger set, in this case, element 5, is now part of the path. Meanwhile, the depth of nodes in the larger tree, such as elements 5 and 3, remain unchanged. Additionally, observe that after a merge, the new set containing the nodes from the smaller set is at least twice as large as the original small set. For example, element 2 was initially in set 2, which had a size of 1. After the merge, element 2 is now part of the new set 5, which has a size of 3. The new set 5 is at least twice as large as set 2. This effect occurs because smart union always merges the smaller set into the larger set. In summary, merging two trees has the following effect on each node in the smaller set. Its depth increases by 1, and the set that contains it becomes twice as large as before. Since the maximum possible size of a disjoint set is n, a node's depth can increase at most O log n times. Thus, the depth of any node is upper bounded by O log n, which also determines the time complexity of the find operation. In practice, the find operation can be further optimized using a technique called path compression. With path compression, when an element I is accessed during the find operation, we update AI to point directly to the root, reducing the depth of the tree. For example, consider a disjoint set represented by the upper forest. Initially, A1 equals 3, meaning the parent of element 1 was element 3. By following the parent chain, we find that the root of element 1 is element 5. To speed up future lookups, we update A1 to 5, making element 1 a direct child of the root element 5. After this update, the root element 5 has 3 direct children, elements 1, 2, and 3. By making the tree shallower, path compression significantly reduced the cost of future find operations. Here is the pseudocode for the find operation with path compression. In line 2, we record the node that is being accessed. In lines 3 to 5, we traverse up the tree to locate its root. In line 6, we update the accessed node to point directly to the root, effectively flattening the tree. It can be proven that with path compression, the find operation can run in O alpha mn time. Here, m represents the number of executed find operations, and n is the total number of elements in the disjoint sets. The function alpha is a slow-growing function that it is effectively constant for any practical input size. While the time complexity is not strictly constant in theory, the actual running time is very close to constant time in practice. Due to the complexity of the proof, we omit the detailed analysis here. In summary, we introduced the quick union implementation for the union find data structure in this video. Conceptually, this approach represents disjoint sets as a forest, where each set corresponds to a tree. Internally, it maintains an array A with size n, where AI stores the parent of the element I. Its union operation runs in constant time O1. With smart union, the find operation runs in O log n time. Further, with path compression, the find operation achieves near constant time efficiency in practice. This concludes our discussion of the union find data structure. Thank you for watching, and see you next time.